Hang on one second, everybody. Let me get this out of the way. Hi there, and welcome to Global Hack Week. I'm so excited that you're all here with us and joining for this session on some ways that we're going to meld interests in machine learning and data. I hope all of you have had a really great weekend, seeing as it's Monday, at least here in my time zone. If you did anything fun on the weekend, maybe you went on a hike or you saw a movie or something, feel free to send in the comments. That would be, that would be nice to build our community a little bit. Hello, good evening, Arc and Highway and Dark Rules. It's really great to see all of you here. And I apologize for the late start today. Getting off a couple minutes late, but hopefully I'll make up to it with y'all with some good content. We're actually going to be looking into classification algorithms, which is something we did back in February on Global Hack Week. So if you're interested in learning about classification algorithms and maybe you didn't get to catch those February streams, it'll be a really great time. Okay, so Sanjay says, watched Oppenheimer. I hope you liked it. I had plans to watch Oppenheimer, actually, but it got to be midnight, actually, when the movie was going to screen, and I got so tired I actually skipped it. Because I think it's, I read somewhere it's almost 3 hours long, right? So it was a little too long for me, I think. But, yeah. As we entered Tuesday already here in India. Okay, well, sorry about that, but at least you're closer to the weekend. That's good. And Josiah says, went mountain biking this weekend. And we have some folks, Usmam, preparing for an ML technical interview. So hopefully some of these concepts will be helpful as you prepare for your interview. And we have some folks in the chat saying they've worked with KNN and things like that. So let's get started actually with our presentation. So excuse me, I have to kind of look underneath my computer to see. All right. That should be right there. And this is what I'm calling our intro to classification algorithms, which is going to be sort of the first part of this lecture series. And before we go even further, I want to just make sure everybody's checked in. And the reason why we're so picky about this check-in thing is because we want to know what kinds of events folks are interested in. And, what's popular, what do you want to see more of? And so by checking in, you're really helping us out there. And, let me actually share that one more time, just so that you have it and it's easy for you to get. This is the link to check in. Ajax says, waiting for some rain here in Tucson. It's been so hot in the Southwest here. So I hope you get a little bit of relief out there. But anyway, just use that link for any check-ins that you might have. And we're going to actually continue on and talk about some of the most common classification algorithms. So I have 7 algorithms posted on these slides, and we're not actually going to go through all of them, but we're going to cover at least a few, maybe even 2 today. We'll see how far we get in our 2-hour session. Maybe even 3, who knows? But these are some of the most common classification algorithms. So if you've ever dealt with regression before, linear regression, we also have logistic regression, which if you've ever seen a logistic curve, it looks a lot like this, like an S. And so you can have points on one side of the logistic curve and points on the other side. So that would create kind of a binary there, and you could classify things in that way. You could also use naive Bayes algorithm and k nearest neighbors, which actually someone in the in the chat mentioned k-nearest neighbors and having used that before. Someone says, and actually today we'll do a little bit of we'll do k-means clustering, which is line number 6 here. I heard in the chat, shout out for SVM. I know I'm taking these in a little bit of a, chaotic order here, but that's this last technique here. And someone else says Markov decision process. I've never heard of that one. That one is actually a little bit less common. It's quite common for some robotics applications. So we will actually get into that one a little bit. But yeah, if for just a little overview, in case you're wondering where are we going to be going with this, I want you all to be able to use these algorithms in applications that you care about. And so we're going to do some test cases where I just show you some ways that these algorithms can be useful given some sample data. But really, if you want to take it in any direction you'd like, that's totally up to you. Once you know how to implement the algorithm, your choice of data and problem is really up to you. So we're gonna work on that. And Axu says MDP can classify. I thought it was only for RL, which stands for reinforced learning. It is. So actually, learning is different than classification versus regression. So classification simply means that the task of the algorithm, the objective of the algorithm, is to classify data in a discrete way. So you're saying this or that. And so Markov decision process, we can classify, we can make a decision like move this way or that way, turn on this process or turn it off. So we can use Markov decision process for classification. And so, but yes, you are correct. Reinforced learning is a very good point. And Tinson says, how to know what machine learning algorithm type best matches the functionals and unfunctional use cases to the operational scenarios for a project app. And so this is sort of some of the concepts we'll be talking about today. But before we get too bogged down in those details, I wanted to ask you a few, get to a few basics of what we're doing here. So I want to talk about what is a classification algorithm, because just make sure we're all on the exact same page. So a classification algorithm will take data, which is features. It actually doesn't necessarily have to be raw data. We could clean it and organize it into these features. And then through the classification algorithm, we can produce discretized output. So for example, meaning that there's only certain fixed number of options. So this classification algorithm here is what I call a fruit classification algorithm. And it takes these features and processes them into a pair. So let's say, for example, that the color was green. The size was about the size of your hand, and the weight was maybe 200 grams or something. I guess that's kind of a light pair, actually, kind of a small pair. But then the classification algorithm could select pair based on that information, even though maybe the weight is a little small. The color would give it away, and maybe apple could also be green, right? So that is a good point as well. I had a request to share the slides in the discussion window, and I'm totally happy to do that. So I'm going to go ahead and send those now. I'm hoping that it's not on edit mode. Let's see. I'll check real quick. Just give me 1 second. All right, anyone with the link can now view. So you should be able to see that. And it looks like folks are able to join now. I'm sorry if it wasn't open at first, but you should now be able to see. All right. So hopefully you can check that out. And yeah, so like I was saying, I mean, this classification algorithm can take data that's not necessarily um, cut and paste. Oh, this is an apple. This is a blueberry. The data is often incomplete information about exactly what the fruit is. I mean, just because we know the color of the fruit doesn't necessarily mean we know what it is. But if we have enough features and enough data, this classification algorithm can learn over time to sort that feature data into discrete outputs, okay, and improve its accuracy. Right? Here's another example. And I know I wrote this as an email spam class. I actually mean that this is a decision algorithm here. So we had a question in the chat about reinforced learning. And, reinforced learning is actually the process by which this algorithm improves. And so it learns. And so that is definitely an element. But really, this is a classification algorithm here. So look, data, time of day, traffic levels, food in the fridge, and hunger level. So imagine that I'm at home right now and I want to decide, should I stay home or should I go grocery shopping? What are the different features that I would want in order to learn here? So we could say time of day is you know morning time, 9 a.m. Traffic levels are low, and food in the fridge is extremely low, and my hunger level is high, right? That would indicate that we should go grocery shopping. And here's a final example, which is an email spam classification algorithm. And so this algorithm is deciding whether to classify a given data as spam or not spam. And so this email that we get, which is our data, has several features. It could have a sender feature, a send time feature, a subject feature, and a body feature, for example. And based on that information, it could make a decision as to whether to show you the email or not. All right, so these are just some examples of how classification algorithms can be useful. And I'm actually going to pause for a second to answer some questions in the chat. So, as far as agglomerative clustering for speaker diarization, I actually don't know about that. So maybe someone in the chat might be an expert on this technique, but I'm sorry to say I don't know about this technique. And Chandrasekhar, if you are a beginner, that is totally okay. This is intended for beginners. Hey, Crystal says, why is classification important? From an ML beginner. Well, I hope that some of these examples gave you a sense of why classification might be useful. And yeah, a lot of regression algorithms you can think of as a classification. You can kind of switch their use case back and forth. For example, there is a random forest classification algorithm, which is over here. And if you learn the classification algorithm, it becomes easier to understand the regression version. And regression is the other large category of machine learning models. Now we also have lots of deep learning models, which none of these would classify as deep learning models, I suppose. But anyway, it helps you to understand other machine learning algorithms by learning these classification ones. So there's multiple reasons why it's so important. And Ipisako says, where can we see the past videos? They're all on our YouTube channel, which I'll send over a link to that. Yes, so all of our workshops are recorded on the YouTube channel, including this one, and including our workshop from February, where we went over some of these concepts. So if you're interested in all that, please feel free to check them out. And we will actually be going over a clustering algorithm today, Osmam Hadir, and that actually is somewhat different than a classification algorithm, but it does produce discrete uh, sort of outputs. So that's why I've included it in this classification workshop. So Viraj says, what is the difference between regression and classification? Well, classification is these sorts of problems that we're talking about today. For example, uh, classify some fruit if you know data about the fruit. Make a decision of whether to stay home or go grocery shopping. Make an email decision of spam or no spam. But let's say that instead of choosing between 2 or 3 or 10 discrete options, I wanted you to, based on a bunch of data, I want you to guess the speed of an airplane. Okay, so you know how far away the airplane is from it's from the airport. You know the weather conditions at the time. You know its altitude. You know what kind of plane it is. And I want you to guess what is the speed of the plane. Well, if you wanted to predict the speed of the plane, you could create several categories like slow, kind of fast, crazy fast. But really, you might want to predict a number like 360 kilometers per hour. That might be more useful for you for some reason. And so that would be where regression algorithms come in. And yeah, if you all are interested, we can do some regression algorithm practice this week as well. That would be totally fine with me. We're just starting with some classification ones. Okay. So that's sort of the idea there. And actually, Osmom has a great answer there. It's a predictive of a continuous value. So the value could take on any, it could take on any value, the predictor, the predicand. And as far as how to know which algorithm to use, it depends on your use on your use case. If you wanted a number or a category. And we had another question about the schedule for this week. And actually, the schedule is going to be on our website. So let me send that to you, actually. It's called ghw.mlh.io/schedule. And you can actually add this to your Google Calendar, which is pretty cool, right? Yeah, it'll be really interesting. And actually, I think later today, we will be having a second machine learning track, and with Will, and you'll be doing some Kaggle competition. So if you are interested in more machine learning, I highly recommend that workshop as well. I'll send the link in the chat. Maybe some of the things we learned today will be applicable. I don't know, but now we're going to move on to how we construct an algorithm specific to our needs. And this is super important subject. And it seems like it has come out of a lot of questions in the chat as well. So we're going to address that next. So first, we want to talk about the type of learning involved. And so we have this diagram here, which is supervised versus unsupervised. It's sort of this classic Venn diagram that you'll see sometimes. And in a supervised case, models learn from training examples provided by humans. So in our grocery store example, let's say that the model learns to classify fruit because we give it images of the fruit and we actually have a human look at the image and tell the algorithm, this one is a pear, this one is a blueberry, and so on. This supervision technique is mostly used for discrimination tasks. And in this context, discrimination actually really should be called recognition tasks, but both are used in the field. And so it just means to recognize something, which is similar to the grocery store example. And hey, Crystal says, will we practice this through a project? Yes, we will. We will practice through a project after this presentation. And so typically we would split the data into training data, which is where the model will calibrate itself based on the human provided tagged data. And then 20% of the data will be used to test on. So those are images that the model's never seen before. They're totally out of the sample. And that gives the model a way to kind of test its learnings and see if it really figured things out. It's a lot like how you might learn in school. Like if you do a lot of math problems from the book. I don't know if folks do math problems from a book anymore, but then you could take a test, and the test is questions that you've never seen before. And if you do similar, if you do similarly to how you did in the book, that means that you learned. So that is the idea here. I also have some material on random forest that we may get to with this sort of idea. Yeah, so here's our apples. You can show many different pictures of an apple to an algorithm, and maybe it would eventually learn how to recognize that. Okay, so now we're going to move on to another type of learning, which is unsupervised learning. And actually today we're going to look at an example of unsupervised learning. So this is the opposite of the previous case, where the model is learning from data that is totally unlabeled. There's no human input into this process, except for obviously the way that we've designed the algorithm and the type of data that we expose the model to. And it's mostly used for generative, or another word for generative is imagination tasks. Okay, so actually ChatGPT is an example. And there's no split between train and test data. In a sense, we're not testing against anything. There's no human test. Although with ChatGPT, there is sort of a test built in, and most real-world applications do have some sort of test in them. But today we're going to be looking at one with no test involved, which is the k-means clustering algorithm in Python. And so here's an example. We can tune parameters of the model, such as eyes, age, perspective, and mood, and we can generate an image using a generative adversarial network, for example. And once again, this algorithm in particular, a lot of the algorithms like ChatGPT are extremely complex, have many, many different parameters that are tuned actually by a secondary algorithm that validates the performance of the model. But just in our case, we're going to study a more simple algorithm. And now I'm going to talk about reinforcement learning, which is that third category of learning. And this is when the model learns the best strategy using a scenario given by humans. So in this case, we are sort of giving the model a lot of information beyond just the data itself. We're actually going to tell it some of the possible outcomes and some of the rules of the road. And by that, we're going to not exactly label our data as correct choice, incorrect choice, but we're going to give it some sort of human input. And so the scenario is sort of what actions can you take as an actor in this scenario, and what's the environment? How is the environment can respond to those actions? So we'll learn about reinforcement learning and use our Markov decision process algorithm for this one. And like I mentioned at the beginning, this is mostly used for decision-making tasks. like robotics. And Bugbreaker18 says, what is semi-supervised learning? Got asked in an interview. I would classify this reinforcement learning as a form of semi-supervised learning. Yeah, and any time when you're giving the model some human guidance, but you're also letting it learn on its own, is, I would say, semi-supervised. So yeah, this is just more information on Markov decision process. This example, the example that I give on this is highly based on this computer file lecture, which I really recommend you check out. But yeah, so here's actually a diagram that might help you to understand this. So Bugbreaker18, you can see unsupervised is this category here, where it's a purely imagination task. Let's say you're asked to imagine a creative writing piece or a picture of a dog standing on Mount Everest or something. That's an unsupervised application. And the supervised application is when you're asking purely for recognition. Oh, do you recognize what this image is? Do you recognize my voice? Like when you say, "Hey Siri" to your iPhone. Oh, that set off my iPhone. I could have predicted that. But these categories in the middle here are semi-supervised. You're asking for translate a language, describe an image. These are things where you're telling the model, hey, look, these are the rules of the grammar of this language. You can't say this, you can say that. But then you're kind of giving it some leeway on how to exactly translate the phrase. That is a semi-supervised application. And yeah, this reinforcement learning thing would be another example where you're not telling it, how to deal with every case. You're sort of giving some framework of constraints that the model must have. And then within those constraints, the model imagines the best strategy, generates the best strategy. So hopefully that is a good Venn diagram for your question. Hopefully that helps folks to understand a little more about this supervised, unsupervised thing. Okay. And so here's some other factors that you might want to consider when you're constructing your classification algorithm. For example, the number of features. How many variables do you have? And so when you have so many different features, certain algorithms are optimized for that use case. So a support vector machine algorithm, or SVM, is really optimized for that case. On the other hand, a decision tree is much less optimized for high numbers of features. And so and is much more interpretable when you have just a few features. So this little box up here asks, can you reduce the number of features to simplify your model? And in many cases, you actually can. So you can pick out features that are actually meaningful. I mean, for example, let's say you're trying to predict the weather tomorrow. And one of your features is the weather from today. Well, that's really relevant to the weather tomorrow. But if another feature of yours is what you ate for breakfast in the morning, that feature is not going to be very useful. It's not going to improve the skill of your model. So some features have more value, predictive value, than others. It's not just about having the most features possible. Another factor to consider is linearity. And so if your data is linear, we'll consider a support vector machine type thing. Non-linear, you might want to consider decision trees. So I've put the same algorithms up here, but they deal with linearity in different ways. So this means I'll actually get into this a little bit later. So before I explain what is your data and why is it linear, we'll talk about that in a moment. So Viraj says, what exactly makes the data linear? By that I mean if there are if the relationships within your data can be you undergo a linear transformation to be interpretable. So we'll talk about that in the project. And support vector machine is this diagram is really good at explaining this. So essentially, you're using this plane. You're asking the algorithm to construct a plane like this red line here. Let's imagine these two features, x1 and x2, are like what's the the color and the age, or the color and the size of the fruit. Maybe these blue dots are blueberries, which have really small size on x1. Let's say x1 is the size, really small size, and they're very blue in color. So they would lie on this side of the red line. On the other hand, let's say x1 is size, right? So very big size and small amount of blue shading. That would indicate an apple. So this is sort of just a simple diagram. You could have many dimensions, and it will scale linearly, which is really nice for our optimization here. All right. So we will discuss this later about linearity and things like this, because we're actually going to deal with the clustering algorithm, which is an algorithm that deals with linear data. And we will see how transforming the data can help us understand that. We're going to go from a polar form to a rectangular form of the data, and it'll really improve the algorithm's performance. Right? And here's another example here. So training time. How much data do you have, and how fast is your computer? And so you often cannot really change these. If you want more data, oftentimes you don't have it. Or if your computer is, the one that you have at your university or in your company, oftentimes you can't just buy a new, faster computer. And sometimes it's not even feasible to do that, even if you had the money to do it. So in that case, you want to consider what the training time of your algorithm is. So for a faster training model, logistic regression is extremely fast. However, random forest, which is actually an ensemble of decision trees, this can actually take a very long time to train. And of course, when we get into more complex deep learning models, Axis mentions computer vision models with CNNs. Yeah, that can be really difficult to train. So, actually, sometimes requiring special processors. So, this is just all to say that training time is often a very major factor in your machine learning algorithm development. Here's another factor to consider: the number of parameters that you might have. So, how much flexibility do you want in your training? With less parameters here, I'm looking at logistic regression, which has 4 different parameters for the regression model. With more parameters, you could have something like k-means clustering, which you can really fine-tune the parameters of. And this can just be a matter of your preference and also a matter of effectiveness. Sometimes more parameters can mean a more effective model. Other times, it doesn't actually make that much of an improvement. So it's up to you to kind of figure that out. And you may think one model is more interpretable or more applicable to a certain situation, and the parameters are easier to tune. Another way you can think about this is by splitting your data. So you can split it into train, not just train and test, but also train, validation, and test. So this is almost two stages of training where you are going to tune the parameters first, then tune the hyperparameters, which are these that we're talking about here, and then, yeah, test the model for performance. Okay, we are going to take a break, actually probably only five-minute break, because I want to get to a few more things. And then we're going to do our k-means clustering example. Yeah, just stay tuned for that, and I'll see you all in 5 minutes. Let me answer some questions before I go, actually. I just want to make sure that I got everybody's questions. As far as looking at random forests, we absolutely can do that. Maybe we will do that today as well. But anyway, all right, I'm going to give you all a quick break, and I'll see you after the break. Hey everybody, and welcome back. Let me just change the slide real quick. Um, Actually, before we get into that, I just want to address a few of these questions and see if anybody on their break was able to grab was able to classify some fruit in their fridge and grab it for a snack. I grabbed this peach here. Um, so yeah, definitely make sure you're taking care of yourself during Global Hack Week. It can be a lot of streams and a lot of learning. So make sure you're hydrating and eating food. Um, Always good to remember. Okay, let me check out these comments. What reminded me of that is, hey, Crystal said, go for some cherries. Yeah, why not? Cherries I think they're in season actually here. Um, then we had a question, what is hyperparameter tuning? So hyperparameter tuning, it means that before you test the model, you adjust the parameters of the algorithm itself to try and see whether there is a better option. So I'm actually going to look at one of these examples. I'm going to go to the documentation for this one. All right. Hopefully you all can see my screen here. All right. So here's random forest classifier. And you can see that the object here, which is written by scikit-learn, so they've already implemented this algorithm, but it has many different hyperparameters. So one of the hyperparameters is the number of estimators. This is the number of decision trees in the random forest. So you might remember from the diagram we had about random forest where there's a branching of many decision trees. This defaults to 100 decision trees, but you could easily change it to 10 or 1,000. And maybe by changing the number of decision trees, by increasing that number, you could potentially get a more accurate model. And so that's the idea with hyperparameter tuning, is to, before you test and evaluate the performance of the model, see if there's anything you can change about the algorithm itself that's going to somehow improve your performance. Hopefully that helps. And then there's another one here. Oh, yes, and Fizz09 made a very good explanation. In the k nearest neighbors algorithm, the value of k could be a hyperparameter. So this is how many neighbors are you going to consider? And so we have an example here with the example of trying to determine if something is a pear. With supervised learning, if you had a fruit basket with 2 pears in it, would you have to label each pear as a pear? Would it screw up the training if only one was labeled? That is a very good question. Yeah, I'm not really sure that I know whether it would screw up the example. I think it depends on the amount of data that you have, because if you have enough examples of baskets with 2 pears in them, the model should have no problem identifying that as a pear, even though there's another pear in the background, right? Let's say this is some computer vision model that's looking at images of pears. So yeah, that's a really good point, though. I'm not sure. I think if the object isn't labeled, then this is sort of a different but related question. So yeah, I mean, if your data is not labeled, then it won't take it into account. So the algorithm will only consider data that's labeled. And hey, Crystal asks, where are we right now? We talked about supervised ML and other learning and some factors of what you might consider. Where do we go with k-means clustering? That's a good question. So we're actually going to go into a project, a real life project here, just an example. with some real data. Okay, and yeah, if any data sample is not labeled, then it's not considered for learning. That's right. All right, so hopefully this answers a few of your questions, everyone, about hyperparameter tuning. A lot of these hyperparameters are super specific, and you can actually learn about them in the documentation of, hey, what does this hyperparameter even do? So I highly recommend, if you're interested in hyperparameter tuning, look into that a little bit. Okay. Now I'm going to present my screen. We're going to go into our, we have about 1 hour left. We're going to go into our code editor. And we're going to pull up some files here from, let's see. Sorry about this, everybody. Just trying to get everything set up for you. So, by the way, before we continue with this code, I wanted to give you a little bit of an idea of what k-means clustering is, since we only talked about it briefly at the beginning of the workshop. Essentially, this is a clustering algorithm. So it's similar to a classification algorithm in that we're giving discrete categories to the data. Think about this example on the right here. You have these 3 categories: yellow, blue, and red, and these categories cannot be continuous. So there's no like purple or green shade. They're all just 3 different categories in this example. And random initialization means that each answer will be slightly different each time. So you can actually choose where you start these markers, these X markers. But the default setting for this algorithm is to randomly place those and see how they evolve. And each iteration of the k-means clustering algorithm works to minimize the squared errors from a centroid. So that's what makes this algorithm sort of rectangular in its data structure. So if you double the distance here, that will be accounted for by the algorithm by also doubling the distance from the centroid. So you can kind of think of this algorithm as trying to draw an oval around the data in this rectangular way. So that's what I meant earlier by you want to make sure that the data is actually fitting the algorithm itself, and we will look at an example of that. Okay, so over time, with iterations, we are reducing the error on these terms. Okay, so here are the k-means clustering assumptions, and we always want to look at the assumptions of our model before we implement that. And the first one is that we have k clusters, each of roughly the same size. So we're kind of trying to think of, okay, can we see how there might be 3 clusters here? If we say k is 15 different clusters, it may get less and less meaningful over time. So we want to think about that. The second point here is that features are isotropically distributed, which means like they look similar to a sphere. So that goes with the third point, spherical variance. And there's flexibility in many of these assumptions. So the algorithm can also often do quite well on data sets that violate these assumptions. But you just want to have them in mind so that you can sort of account for them when you do your analysis. Okay. So someone says, don't quite understand this algorithm. What is it used for? Well, we're going to do an example. So this example is on my GitHub page at this link. This link is available also in the slides that I shared earlier. I'm going to paste it in the chat so that everybody has access to it. So here's the link. And when you go to that link, you'll see a Jupyter Notebook, which is a really great resource for learning. And you'll also see some data in the data folder, and you'll want to download that too. We actually have two different data sets. There's our bullseye data set and our faithful data set. And you'll see quickly that these two different data sets, one is rectangular and one is not. And so actually, I think I should really change the slides and then talk about rectangular data as well, and just the general character of your data, looking at it before you implement an algorithm. All right, so let's go to our Visual Studio Code editor. All right, share this with all of you. You can see here, this is my Visual Studio Code editor. If you do not have a code editor, then it's really simple to do this also in your Google Drive. So if you have a Google Drive, you can set up a Google Colaboratory, and I highly recommend this as an alternative resource. So I'll send a link to Google Colaboratory in the chat. If you want to use Visual Studio Code, you can also do that. It's just going to take a little bit of time. But yes, if you want to download the data, that would be really great for this workshop. All right. Are the Jupyter Notebooks viable for this workshop? Yes, they are. We're going to actually be using Jupyter Notebooks, but you're welcome to use PyCharm. As far as following you in code, you're certainly welcome to. If you think that will be helpful for your learning, you're also welcome to just watch along and ask questions. Don't worry about missing anything or having to catch up with your code, because the solutions are posted on GitHub. So there's nothing that you need to catch up with. And of course, the workshops are recorded too. So it's totally up to you, however you'd like to follow along. But yeah, we're going to actually code up some of these examples now so you can see some of this in action. Okay, so we have our k-means clustering algorithm tutorial today. That's what we're going to be starting off with. I'm going to change it to a markdown cell. And first, we're going to import the necessary libraries. Okay. So I'm going to import this library called pandas. And this is great, great for data tables and manipulating your data. And I'm also going to, let me change this to code, Python code. We're also going to import NumPy .np throughout the project. And this is great for manipulating data. We'll import matplotlib.pyplot as plt. It's great for plotting the data and or visualizing it. And finally, we're going to import our k-means package. So we're not going to write the k-means clustering algorithm from scratch because somebody has already done that for us. Oh, sorry about this, everybody. Let me select a different kernel. Just use my base Python kernel, should work for us. And yeah, we're going to do a standard k-means clustering example, which is pretty well known. It's an article. It's based on an article originally published on RPosts, which is for the R programming language. But all of the material will also apply today in our Python example. So we're going to load in data from the Faithful Geyser, which is in Yellowstone National Park. We do that by typing read CSV. In pandas, it's a method that we can use to read information from a CSV dataset. So you can see that the Faithful datasets right here, CSV stands for comma separated values. And so we're separating each data into two different types. We have our eruption, which is the length that the eruption happened, and waiting, which is the amount of time it took between eruptions. And just to give you a sense of what this looks like, I'm going to actually show you a little bit. It's kind of a cool thing. Share that real quick. Yeah, I just looked up some of these. Tons and tons of people go. This is actually America's oldest national park, and it's also one of our most popular for visitors. And there's this attraction at the park called the Old Faithful Geyser, which is a natural geyser, and it is often erupting, and folks can observe it. And so this data set is of eruptions from this geyser, and seeing exactly how long it lasts and how much time passes between eruptions. Okay, so we're gonna look into this whole thing and try and categorize that a little bit. And Pugbreaker says, please share the link of that article. Of course, it is in the repository. So I'll send the repository to you, and you can check it out for yourself. Actually, if you prefer working in R, it can be really good to look at. Okay, now let's go back to our example. So we're going to be using this Faithful data set, and we can actually make a scatter plot of these eruptions. So we're going to plot the eruption time and the waiting time. I'm going to add some labels to this plot so that it's easier to see. On the y-axis, we've plotted the time between eruptions, seconds, or I actually believe in minutes. And on the x-axis, we'll say time of duration of the eruption, also in minutes. And the title we'll just say is Eruptions from Old Faithful Geyser. So here's our data visualized. You can see why it's really helpful to visualize data from this example, because you can notice that it's clustered in two different regions. We have examples in this bottom left corner, which are eruptions that are short and happen pretty frequently in between each other. And then we have these eruptions which are longer. They last like maybe 4.5 minutes, sometimes even 5 minutes, and they come much less frequently. So we have these kind of smaller eruptions, you could call them like mini eruptions, and these bigger eruptions. And so we want to know how to classify them. And it might seem obvious for points like this one, which one it should go into. But what about these intermediate cases, which are in this 2.5 to 4 minute range? It's really hard to tell which one they belong to. And so we're going to use the algorithm to figure that out. Right? So first, we're going to convert this data into our features. So we'll type df.values to get the features as a NumPy array. This is the raw data. Okay. And then we're going to build a k-means object, which can take in this data. So we'll define a new k-means object. And we're going to give it several parameters. These are the hyperparameters in a sense. First one being the number of clusters. We're going to choose 2 because we suspect that there are 2 different kinds of eruptions. Init equals random says that we're going to initialize the points at random places. And so that is a good way to try that. And if you wanted to actually make sure it has the exact same result every time, you can specify a specific initial point. 2 times. Thanks. I hope you like the demo. You'll see where we're going with this. And so now if you type in k-means.fit x, which fits the algorithm onto our data, you see we get this algorithm object as our return. So it's telling us that it was successful. This is kind of interesting. Future warning. Okay, so it's gonna change the hyperparameter default. It looks like later in a later version of k-means, but that doesn't concern us too much for now. Instead, we're going to look at the result of our fit, and that's going to be our next cell here. To do that, we're going to actually get these flags. And these flags are kind of telling us what are the labels. So we accessed this label attribute of the k-means algorithm. And the reason I call it flag is because, it's basically saying 0 or 1. You could call it whatever you want, but this is just the output. Let's just call it the output, maybe. So 1 would be our category 1 eruption, and 0 is our category 0. How can we tell which one it's referring to, though? Unfortunately, we can't until we actually visualize it, because this is an unsupervised algorithm, so we didn't actually tell it which ones are short and which ones are long. We just kind of hoped it would figure that out. And hopefully it did. So now we can actually specify a category 0 eruption being an eruption in our data frame where the flag is 0 or the output is 0. Category 1 eruption is where the output is 1. So we're masking our data frame to choose those output 0 and output 1 labels. Okay. So now we can plot this data. So we're going to plot it just like we did before. So instead of using df, we're going to use these category variables. Call this a category 1 eruption. Do the same with our category 0 eruption, sorry. Do the same with our category 1 eruptions. All right. Add a legend so we can see which one's which. And I'm also going to copy the labels from our original plot and stick them on this plot. So now we're going to run this one. And this is our result. You can see that the algorithm has classified the eruptions. And actually, these border cases would be kind of hard for you to tell which one is category 0 and category 1. So the algorithm is giving us a very unbiased way, or maybe you could just say a way that is, there's clear mathematical justifications for this way of classifying them. It's not extreme, it's not subjective, except in the fact that we chose k-means. So, given any new eruption that happens, we can instantly classify it as category 0 or 1. We don't even need a human to look at it and make a guess. Right? So let me just answer some questions in the chat. Bybov says, hello guys, my first time here. Hope that I'm not too late. You're definitely not too late. Don't worry. I'll send you a link to our Jupyter notebook that we're dealing with right now so that you can follow along. We're looking at the clustering algorithm. And of course, you can tag me on like to connect on LinkedIn. I'm always open to that. I love connecting with all of you and seeing all kinds of amazing things you all are doing in the tech space. And so, yeah, anyway, this is sort of our classification here. Does anybody have any questions about this? I see one question about what centroids are. It's similar to a circle. It means the center of the data. So you can kind of think of the k-means clustering. Actually, let me see. I think there might be like some kind of GIF I can look at here. All right. Yeah, I found a good GIF for us to look at. Hopefully you can see that. But basically, these black crosshairs are the centroids of the data. So it's minimizing the distance between the centroid and all of the data in that category. So this is essentially what the k-means clustering algorithm is doing over its many iterations, and it just keeps iterating until the errors start getting small. And then once you finish that process, you have an algorithm that can easily sort the data, any new data, into these 3 categories, or however many categories you'd like to have. All right. Oh, sorry about that. I really meant to share my screen. All right. Sorry, everybody. Sometimes I do this, and I know it can be frustrating for you all as much as it is for me, but just remind me in the chat and I'll be happy to share. But this is the GIF I was sharing. as you can see, it's sort of optimizing the distance between the centroids and the group of data that's there. And exactly, it's a loss function optimization. It's a loss function minimization. So if you've ever heard of linear regression is another example of a loss function. The loss function in that case would be the standard squared errors, the sum of the squared errors rather. And here you're doing the distance, the sum of the distances. All right, great. So glad that's clear. Now we're going to continue, and we're going to do a new eruption actually, and see if we can predict a new eruption. All right, here we are back on our code editor, and we're going to have a new eruption. This eruption lasts for 3 minutes and came 75.2 minutes after the previous eruption. This is actually right in our gray zone. So if you were to visualize it here, let's actually visualize it on our data set. I'm going to put a new one here, plt.scatter. We're just going to use 3 at 75.2. Call this new eruption. Okay, so you can see the new eruption is right over here. It's kind of right in this gray zone. And you might be thinking, well, which one is it? Is it a 0 or a 1? And to figure that out, you probably want to use the algorithm itself. So we're going to do that by defining these new variables. Say the new eruption is 3, and the new weighting value is 75.2. And we can use a method in sklearn called predict. And we can give predict as many eruptions as we want, really, but we're just going to give it this new one. Here's our new predictor. Prediction values. Oh, sorry, I actually need to have this in array form as well. And we get a prediction of 1. And that's actually what I would expect probably. I mean, just looking at this visually, it seems like the line that the algorithm drew is right here. And based on that line, the green dot falls on the category 1 side. But yeah, without this algorithm, we would not be able to predict so easily. Right? And now we're going to do a non-spherical clustering example. And this goes back to that situation where we're saying, what if the data is nonlinear? And we don't want to know just, is it a high, it doesn't really make any sense to ask, oh, is it high waiting period or low waiting period? And we can draw a simple line between them. So for this example, we're going to use our bullseye data. So you want to type data / bullseye.csv. We're going to only take columns X and Y from this data set. Okay. So from this data set, we see that the X and the Y, these are actually the X and Y positions on, let's say, a piece of paper of a bullseye. Maybe you are throwing darts at a bullseye and making little holes in the paper, and these are the locations, you measure them of those, and so let's plot them actually to see what we get, just like we did before. And we'll title this plot bullseye. hits. So here's our bullseye hits. So we have these 3 different rings. Maybe the outside one is worth 5 points, and the middle ring is worth 10 points, and the center ring is worth 15 points. And these are the results after many, many hits from different players on our bullseye board. Let's say we want to build an algorithm that will automatically calculate the amount of points that a user gets based on where they hit in the bullseye. All right. Well, we can do that with a clustering algorithm. So let's try implementing this. We have 3 different categories. So in our k-means object, we will define the n clusters hyperparameter to be 3. The initialization will be random. And the maximum iterations will be 300. We're just going to say that to limit the amount of iterations that the algorithm does. And let's fit our algorithm to the values. So we'll have our category 0. Will be using this term flag, so I'll just keep using this. I might want to change that the next time. We'll have actually 3 categories now: a category 0 hit, a category 1 hit, and a category 2 hit. So now let's plot the categories. We'll write some code that plots these categories. And we'll copy the title from our previous case, and maybe also label X position and Y position. Let's say these are just positions in meters, for example. Okay, look at this. This is our classification. You can see that the k-means clustering classification, it went a little haywire in this example. It said that this is category 1 hit over here, or category 0 hit is here, category 1 hit is here, and category 2 hit is here. But that doesn't really fit our data. And if you look at the data, it's not really rectangular in any way. It's actually polar. So it has this radius coming out of it and this angle as well. So we're going to convert our data into a rectangular case. And we're going to do that to take advantage of the k-means clustering algorithm. And so I don't know if any of you are familiar with this, but we're actually going to do what's called a polar coordinate transformation. You might have learned about this in your math class. You might have thought, wow, when am I ever going to use this? But we can actually use it for our bullseye case. All right, so this is the polar coordinate system here. You basically have 2 different, let me share my screen. You have 2 different parameters. Instead of x and y, those parameters are r, which is the radius, and I guess this is phi here, which we could just say is the angle here. Um, and so you could say any point, instead of saying that this is 2 comma 3, you could, or 2 comma 4, let's say, or yeah, you could say this is a radius of 3 and an angle of 60. And in the same way, instead of saying that this is -5 or something, comma -3, you could say, well, this is a radius of 4 and an angle of 210, right? So that's just how the polar coordinates work. And to convert, we have this formula here, which hopefully you can see. And the radius is equal to the square root of x squared plus y squared. And that's really what we're going to be using in this example. We won't use this phi angle as much, but it will still compute it. So because we want to have two features, just like we had two features x and y. Yes, that's right, high school math. That's what we're getting into. Yeah. So hopefully this is a good refresher, and if not, we will actually go through it we'll go through it together. So let me present my screen again, and we'll work on this polar coordinate stuff. Right. So first, find a new column of our data frame, which we can always do with Pandas data frame, called R, and this will be the radius column, or radius feature. And it's going to be a transformation of our data. It's not a linear transformation, but by doing this, it will make our data more easily accepted by the k-means clustering algorithm. And phi was our angle, and we're going to use arcsine as the conversion for this. Say y over r. So this is the angle feature. So if you don't know these formulas, you can just use the ones, copy and paste the ones that exist in the notebook. I used theta here in the notebook, but we're just going to use phi to be consistent with the example that we saw. And now we can try again with our k-means algorithm. So we're going to do the exact same object, number of clusters here, random initialization. Let's up them iterations. Why not? 400. See if that changes anything. Feel free to play with any of these, by the way, any of these categories or parameters. And we're going to accept two new features into our algorithm to train on, and they're going to actually be R and phi. So now we can look at the results. We'll do the same three categories. Category 0, category 1, and category 2. Might ask, why are you plotting in this X and Y way? Well, you'll see why in a second, because if we plot in the R phi way, it will look a lot different, and we'll actually try that afterwards. Well, I'm just going to copy and paste the labels to save a little bit of time. And I'm just going to specify the location of the legend so that we know exactly where it's going to go. Got an issue here. Wonder why. Oh, I guess I didn't run this cell. Well, let's run this cell first. And actually, maybe we'll look at the data. BFR and BF phi. So the X label is R. Let's say radius. Y labels angle. So this is what our data actually looks like in polar coordinates. So you can see it's going to be a lot easier for us to use our k-means clustering algorithm. And in fact, if you ever have an example where the data is not super spherical, you can always try a transformation like this. It doesn't have to be a polar coordinate transformation, but you can try any kind of transformation to see whether the data will be more easily categorized, as long as you have some kind of reason behind why you're doing it. Bookbreaker says, do we generally need to do that for k-means? Yeah, it really just depends on your data. It really does just depend on your data. Okay. And so, yeah, now we will have a look at what this gives us. You can see in our bullseye now, we get exactly what we were expecting, which is this category 0, category 1, and category 2. You can tell that category 0 in this case is the most valuable 15-point category, and they kind of span out from that. All right. And so let's look at the length of this data frame, by the way. We have 3,000 hits on this bullseye. Let's try and see how many points there are on the board right now using our algorithm. So we will define the central category, which is category 0. Give that 15 points. Category 1, we'll give it 10 points. And category 2, we'll give that just 5 points. So let's define a score. Our score will start at 0 and increment as we accumulate hits. So we're going to go through each and every label and say that if the label that the algorithm gave was 0, we'll add 5 points to the score. If the label was equal to 1, we'll add 10 points to the score. And if the label was equal to 2, we'll add 15 points to the score. Now if we run this code and we print out the score variable, we see that there were 30,000 points awarded to the users. So on average, there were 10 points scored by each hit. Yeah, my M8 Scully says, My mate Scully says, my old enemy turned friend. That's great. Yeah, and once again, this is not something you would need to do every time you do k-means. But it's just sort of to get you thinking about the assumptions of the k-means clustering algorithm. And, what are some of the things you could possibly try if it's not working out? Okay, so I'm going to just post the check-in link one more time for today. That way you have it in case you didn't check in yet. And we might actually move a little bit into our lesson 2. This is going to be decision trees and random forests. And so, yeah, why don't we move into this just very briefly, because we have some extra time, right? So I'm going to actually show you how to interpret this. And we're going to actually give an example of this decision tree of the 2 features, okay? So I'm going to say that start equals 10 and age equals 10. Okay? And I'm not going to tell you what these are yet, but I just want you to follow through the decision tree and see if you can intuit what decision we would arrive at. So if anyone can tell me which number at the bottom, which of these 5 values would we arrive at with start equals 10 and age equals 10? Yeah, 0.14. That's right. Because when you go through this tree, you're going to first arrive at this threshold. And you can call these a threshold. So start at 8.5 is going to be the threshold. And if the start is greater than 8.5, which it is, we move to one side. If it's less than 8.5, we move to the other side of the tree. And so, then we move to this one, which is the threshold is 14. So we go to the right. And now this is an age question. So it says, is the age less than 4.6? No. So we move to the right. Is the age greater than 9.2? Yes. So we move to the left. And then 0.14 actually represents that we want to assign a 14% probability to that one. Okay. So hopefully that helps you to understand. All right, now let me answer a few questions in the chat. First one is, how do you know if it's, quote, not working out? With the bullseye, we can sort of interpret it ourselves, but with a more difficult system, how would I, as the user, know if my result was garbage? Well, that's a really good question. And I think you need to use some sort of expert judgment to discern whether your clustering actually is helping you make sense of your data. It's not really easy to see. I mean, if you are getting really high errors that are not going down after training, that could be one indication. So you saw this plot that we had earlier. Let me show you that slide actually, because that's a really good slide for this one. Just bear with me, everybody, while I go find that slide. All right, here's the slide I was referring to. So look at this. The first iteration is, it's telling me that the squared standard errors which is the total distances in this algorithm, at the start is 6735.8. But then on second iteration, it goes down to 5238.5. And hopefully by the third iteration, it would go down even further. And so if you get a substantial reduction in errors, that means that this approach was successful to a degree. And you're essentially having success in your training. But once again, even if you find success in your training, that doesn't necessarily mean that the result is useful to you. So you want to always be looking at it with whatever kind of expert information you have about the problem. That can also be really helpful. But yeah, looking at SSE and how it goes down, if it goes down very sharply and then stabilizes at a lower place, that's great. But yeah, you must make sure you do not overfit the model. By adding so many different clusters, you could potentially do that. So, okay, and another question is, what's the role of entropy in this? That's a great question. So we are essentially reducing the entropy of our problem. So think about this, or we're reducing the information content of our problem. So in the beginning, we had, in our eruption example, we have so many different times of eruption that you can have: 6, 7, 8, 3. And we also, on top of that, we have so many different kinds of waiting times that you can experience. You can experience 10 minutes, 12 minutes, 15 minutes, 70 minutes, 75 minutes. Well, we're reducing that information to just 2 categories, whether the eruption is a short eruption or whether it's a long one. And so we're essentially reducing the information content. And what that means is really we're simplifying. And hopefully that can help us to make sense of our data and make sense of the world, really. We simplify things all the time. So that's, I guess you could say, is the role of entropy in this problem. Is we're taking a system which has a high degree of information in it, and a lot of that information is not actually all that informative, being that we can reduce it down into just 2 categories. Right. So hopefully this workshop was useful to you all, and that exercise at the end that we did with our random forest, with our decision tree, is kind of a precursor to our random forest lecture. Yes, a random forest is just a bunch of decision trees. And we will be exploring that next time in our Using ML Algorithms and Data workshop series. So stay tuned for that. And yeah, thank you all for joining. And I hope you have an amazing Global Hack Week. Don't forget about all of the other things we have planned for you, including, if you liked talking about machine learning today, including our one with Will later today. So please stay posted for that. And folks are requesting I share social media, so I'm happy to share my LinkedIn. If you'd like to connect, I'm always happy to connect with hackers on LinkedIn. So thank you. And yeah, take care.